Hello, everyone. I'm Miro. If you haven't seen me in office hours, I'm the TA of this class. And I will give the lecture today on key overwriting attacks instead of Nadia. This lecture is basically based on these resources. There has been a recent talk at the workshop by Kenny Patterson on key overwriting attacks, and otherwise it's a pretty new primitive that came up in a few papers this year and last year. Where we sort of exploited key overwriting attacks. I was part of two of those papers. So with that, let's start with an overview of what key overwriting attacks are. So Alex asked me to put this into context. So here is the context. Basically, what we looked at in this course so far, we can categorize in those rough four categories. So we looked at unkeyed primitives, which are, for example, pseudorandom number generators, where we looked at attacks that exploited a low entropy source for the seed, for example, a timestamp that you could guess. Or we looked at dual EC DRBG, which is a backdoored pseudorandom number generator. Or we looked at RC4, which has a bias in the distributed samples that was exploited in the Lucky 13 attack against TLS. Then we looked at hash functions, which are vulnerable to a length extension attacks if you don't implement them correctly, or depending on how you combine them with signatures, that could be a problem, as you exploited in one of your homeworks. Then we have symmetric primitives, where you have a key on both sides of the party and they share the secret knowledge of the key. There, if you use them in a stream cipher mode, then there's a problem if you reuse key stream. For example, the many path problem that you solved in your very first homework, where you get XOR key streams and then get XOR of plaintext and make some guesses on plaintext and verify them by XORing it to the other XOR elements and see whether it makes sense what comes out. There are block ciphers, different modes of operations, for example, for AES, that's vulnerable to padding oracle attacks if you use DTC and if you have feedback on whether or not the on-padding operation was successful. Then we looked a lot at asymmetric primitives because sort of a lot of the interesting cryptanalysis happens in the asymmetric space because you use more algebraic structure to construct your schemes. So one thing we looked at was key exchange, Diffie-Hellman or elliptic curve Diffie-Hellman, which we broke with sort of generic methods that I will put under tools. We also looked at encryption, RSA, the famous example, which is broken if you use PKC as 1.5 padding. You can do a very expensive Leichenbacher attack. Or if you generate RSA secret keys with low entropy, then it's possible that you reuse prime factors of your modulus, and then you can do a remainder tree attack that you implemented here in the mining P's and Q's over. There is also elliptic curve cryptography, which is vulnerable to the invalid curve attack that you just did for homework 7. There's also signatures, for example, ECDSA, which could be vulnerable to non-reuse attacks. And sort of more recently, we looked at more general primitives that's useful for cryptanalysis. Here is, for example, discrete logarithm that shows up in various places, for example, Diffie-Hellman, where we base the security of multiple schemes on the security of a discrete logarithm. And so there are those generic attacks called baby step, giant step, and Pollock-Hellman that can be used to compute the discrete logarithm on certain constraints. Also factoring, there are the number field sieve is the fastest known attack for factoring, and so you can use this to factor, for example, RSA keys that are too small, that are only 512 bits. Just in the last lecture, you looked at lattices and Coppersmith's method to find small roots of polynomials that can be used for a variety of different things in cryptanalysis, and probably half of Nadia's paper are exploiting this fact. And today we're going to look at another one of those tools. So another one, another more general attack technique that shows up in different places that's not tied to a specific primitive like RSA or elliptic curve cryptography, but that can be applied to different primitives depending on how they're used. So I'm putting here products that we're exploiting, because the exploit itself, or how something is vulnerable, is really context dependent on how that specific primitive is used. So it's more a protocol level attack than attacking the primitive itself. So with that, let me see. Someone posted it up. Works for some people also. All right. So yeah, with that, let's start looking into the setting in which key overwriting attacks work. So we have an interactive protocol between a client and a server. In this case, we're focusing on the case where asymmetric cryptography is used, because that's what we exploit in both applications, but it could also occur if you use symmetric cryptography. So it's not necessarily inherent to the setting. But for now, let's assume there's asymmetric cryptography used. So the client generates a secret key and a public key, and then encrypts the secret key under a password. You maybe wonder why would someone do that, but we'll see in the applications afterwards that there are actually good reasons for doing this. And so after encrypting the secret key with the password, the client uploads the public key and this encrypted secret key to the server. The server stores this for the user. And so later when the user comes back, the user authenticates to the server again. Hey, I'm user A. You already stored my public key and my secret key. Please give me those values back. So the server returns the encrypted secret key and the public key to the user. And then the user does something with that. Maybe it's a messaging application. So maybe the user sends some encrypted messages, or it's a cloud storage and the user encrypts some files and uploads this. And so through that, since the server is always on this interaction, you will see some kind of response from the user, where the user tries to use this decrypted secret material. So this is the general setting in which key overwriting attacks work. And the threat model here is that the server itself is malicious. So for example, maybe you trust Google, right? Google is your server. So maybe you're wondering why could they be compromised, or why are we even looking at this setting? But for example, or why could they be malicious? Now, one of the examples is they could be compromised. So there could be a nation state adversary, for example, that sees Google has a lot of interesting data. So they try to compromise some of their servers and then run attacks against users. Or another reason could be they could be compelled to comply with a government, depending on how much trust you have in the government wherever you live. For example, if you're an investigative journalist and you investigate a scandal in the government, it's maybe not the greatest if the government has the power to compel the cloud storage provider to provide you data that they store. So this is the reason why it makes sense that we consider a server to be malicious. But the user might still want to use that service. Even they might not generally distrust the server, but they want to be protected against the case where the server could be compromised. And so in this attack setting here, the server can overwrite the key material that is stored at the server. So the server, in this case here, where we have our pointer there. So you see here that the ciphertext, the encrypted secret key, and the public key that is stored at the server can just overwrite them with any value that they want. And then they will see some result of some computation of the client with that garbled key material. So the goal of this malicious server is to recover the secret key of the user, or maybe some kind of weaker goal like decrypting a message that was encrypted. But in our case, we're actually going for the secret key recovery.
I just want to understand, like, so here you're making the assumption that the user does not perform any sort of sanity check. I just assume, I keep the key, just take it, whatever.
This is a very good point. And in fact, some of the services that we exploit, they don't do any sanity check, and that is a problem.
It's on a user side, right? Because you're in essence returning a bogus key.
Yes, we are returning a bogus key here. But this computation here could also be a sanity check. And then the response could be, no, this is an invalid key. Try to fetch, I want the key again, for example. So a sanity check is a type of response. And there are some of our attacks actually do exploit the result of an unsuccessful sanity check at the user. So we're not assuming in general that the user doesn't do sanity checks. Right, a very good question. So one of the ways in which the scenario differs in different cases is maybe the server can only override the public key, or they can override both the encrypted secret key and the public key. And sometimes the server can control what values will be the result of the overwriting. So maybe if you can overwrite the ciphertext, the server can control what the client will decrypt this value to. Or maybe it's blind. Maybe the server can just do some modifications and the output will be some garbled value, but the server doesn't control what value it is. It will just be something random. So any questions up until now on the setting or the threat model?
Another model, which is the reason I'm saying is because imagine I'm the user. I can write down what I upload. Right. Another sort of attack is where you keep the first, let's say, 10 bits the same, and then you override whatever's left. In the sense, like, let's say I upload my password to you and I get back my password. I want to check if you change my password or not. I probably will look at it first. Factors. That's another.
Yes, it's so the override is whatever the server wants it to be. It's not forced to override the entire key, and we will come back to this. We override part of the key. Turns out to be useful in some cases. Any other question? Right. So let's make this a little bit more formal. What we mean by security. So we're going to construct a security game called or I call it the key overwriting key recovery attack. Or key recovery game. So in this game, we have a challenger and an adversary. Not that the adversary here is the server. So unlike in most other scenarios where the adversary is sort of where the challenger is the server. In our case, the server is malicious. So that one is the adversary. We have a challenger, which is simulating the user in our case, and generating a public key pair, an asymmetric key pair, encrypting the secret key and uploading or giving this to the adversary. Then the adversary can have n interactions with the user, where it can override the public key and the encrypted secret key with any value it wants, and it observes some kind of response for those n interactions. And after those n interactions, the adversary needs to guess the secret key. Yes.
Sorry, do you have more to explain on the attacks? I just have a question to N over here.
Let me finish one sentence and then, yes. So we define security as that there is no efficient adversary that wins this game with non-negligible probability. So that can guess the secret key of a user with non-negligible probability. And we say that the scheme is secure if no such adversary exists.
So yeah, to Alex's question, like if I'm a client or if I'm the challenger here and I notice that, like, let's say that my encryption scheme allows me to tell if the key has been tampered with, is it valid? Like, is that N control? How is N control in this situation? Because I could imagine that if I was a really careful journalist or something and I see that the key has been tampered with, I'll just stop responding to the server outright. And in that case, you'd only have N equals 1, right?
Good question, yeah. So the security that you get depends on which N value you have. If you have an attack for N equals 2, but your implementation already aborts after N equals 1, then it's not a practical attack. I think in that case, you would, for that specific scheme, you would limit N to be 1 if this is hard-coded in the scheme. And then it will not be an attack that breaks the scheme.
Maybe by what I'm implying is, like, in practice, then, like, is the challenger like some actual code that's implemented on a device that may not be doing, even if it does the sanity check, it might actually still be reporting back, like you were saying, Alex's question, it might be reporting back just like invalid N times.
Yeah, so the challenger is specific to whatever protocol you're looking at. And it basically does exactly what the client software that runs on a user's device does. Okay. So it would act in the same way. So it could just abort Like you could imagine, for example, implementing this as response R2 to Rn or just bottom. It just does nothing. It throws away the key for every other interaction if it detected in the first interaction that this is an invalid key, for example. And then you couldn't do any attack if it requires actual responses instead of just an invalid response. Very good question. All right, so I have a question for you. This is something to think about. So I'll give you 3 minutes to discuss this with your neighbors. Do you think that the in-CPA security of the encryption scheme that we are using, so the asymmetric encryption scheme that's used here to encrypt the secret, if that is in-CPA secure, does this imply that the entire construction is also KOKR secure? So it's secure against key overwriting attacks. You don't need to have a proof, just discuss your neighbors with your neighbor.
Yeah, we said look all these up, right?
I'll see what's that.
What is it?
I think that's escape on the very top.
Yeah, in-CPA security is indistinguishable from chosen underground plaintext attacks.
So like
So
adversary,
it's a security game where
just like
the adversary uploads secrets to plaintext to
what is
the challenger, and the challenger encrypts those two plaintexts. And the adversary needs to guess which one of the plaintext was encrypted.
If it is there, let me see the KOKR.
The adversary gets the encryption. The adversary gets the ciphertext, and it needs to guess which one was encrypted. And that's how we form a security. Because you can't tell. Or nothing if it's
exposed to plaintext, right? Like R is like this. The adversary is allowed to guess.
Is it gonna be encrypted under PW?
Yeah, like
it's unencrypted under PW. Or key.
just changing the key for a bunch of stuff now. And like, yeah, the final question is, can we get the key?
No idea.
I don't remember either what is like in.
It's not.
So what's the opposite, right? This is like chosen cipher.
I don't see where it is.
We don't know what the plain text is. We want to learn it. But we can give the cipher text. But I feel like I still
But like, what's the in part?
you're
ID or
So it's
what is it different from just CPA?
It's chosen when the.
yeah, no, sometimes you just leave it away, but
Okay,
its support name is.
Oh, okay.
So let's see, I can guess that's
It's like, no, that's not.
Oh, okay, so because right now you're standing back,
Like in the other world, wouldn't
standing back, so you want to
hash or something go wrong.
It's a key derived from
Yeah, like
No, it's usually.
the thing is like yeah, like in CPA secure, you don't change the private key, like the private key remains the same, right? Like here, I guess, like if they're away, like
The adversary here has no access.
some.
I don't know which one.
Here.
They're on the same.
No.
Sort of assume for now that
It's like the private key random, like shouldn't be any way to
And then here.
yes. Like
I heard like.
What we were saying is that this feels like the opposite of CPA. It feels like chosen cipher text.
yeah, the adversary has no access.
cipher
Yeah, since we can change what C1 and P.
No, it's like an extension because you can change also the key, but you can.
All right, I think it's time to get back.
I think it should be.
So, does anyone want to make a guess whether this is true or not?
Like I think if like your encryption method behaved any differently under a choice of a key, then like that that would like it feels like that would leak some information. Like if like the choice of the key were to like change the behavior of your encryption method, then like this would leak some information. So like it makes sense that yeah, like by maybe changing the private key should not maybe like meaningfully change the actual behavior of the algorithm. So I think the answer is it does imply it, I think.
So you're arguing that if ENC is not in TPA secure, then it would also be not KR secure. So because you're arguing if changing the key would leak something about the encryption, which is not in TPA secure, then the construction would also not be secure. Okay, so if you're doing that, then we're trying to prove the inverse. We're trying to prove if it is secure, then the other one is secure, and you can do this by proving the contrapositive, which is if it's not KOKR secure, then it is also not in CPA secure. So you would start with a different assumption.
Yeah.
Does anyone? Well, let's see if someone else also has some thoughts. Anyone else want to?
Question.
Yeah.
So can you play, like, given the two ciphertexts, or I guess, can you play this game twice, or do you just play it once?
You play this game once, but you can choose your ciphertext adaptively. Like you can choose the overwriting of the ciphertext here in this interactive round multiple times. But if you play it again, the challenger will pick. Oh, I find this. Okay, the challenger here will pick another secret key, so it's independent in this game. All right, let me resolve this. This is actually not true. And the reason for that is a bit technical, but so we're proving the contrapositive. We're saying that if this scheme is not KOKR secure, then we're showing that the encryption is also not in TPA secure. Are we trying to show this? But the problem is, so we would need to be able to show this to show this implication. Well, the problem with that is if the scheme is not KOKR secure, then that means we have an adversary that breaks KOKR security, and we want to use this to build an adversary that breaks in TPA security of encryption of ENC. But the problem is for that, you need to use this KOKR adversary as a subroutine. And for this subroutine, you need to simulate this part here, where the adversary sends you some modified ciphertexts, and you need to do some computation on the decryption of the ciphertexts. So you already need to be able to decrypt ciphertexts before you can break in TPA security, which is recursive because it means you already broke in TPA security. So we can't do this argument here. And that is sort of a bit more on an intuitive level. The proof of this is a bit more complicated if you work it out. But on an intuitive level, this tells us that the interesting part happens in this interaction here. Because of this interaction, it's much harder to be KOKR secure than just in TPA secure. It's not enough that you have a good encryption scheme. Somehow this interaction leaks information more than the normal encryption would do if you just have an TPA security game. And that's how we break schemes, because of this interaction.
Well, I don't know if you're gonna go a bit more into detail of how the argument goes in like the general case of going from like the naive construction doesn't work to like any construction won't work, and like in the sense that you said like we would need to construct from like how do you formalize that thing of like this model is like, yeah, I don't know, giving us like, assuming that we can have like more information or whatever. Yeah.
I'm not going into more detail on this, but I'm happy to discuss afterwards, for example. All right. So let's go back to the definition. What does efficient mean in our case? Efficient here means efficient in practice, or that's what we care about, which means mostly minimizing these set of interactions. As Cole also hinted at, if you only have, if it stops after one interaction, then you already have a problem. So a better attack is one that works in only one interaction. And it's possible that those interactions require the user to actually do something, the user to enter their password. So if you have 5,000 interactions, you need to have a really patient user to enter their password 5,000 times before they're compromised. So you want to minimize this number. All right. Are there any other questions before we look at concrete examples?
So in that game, the responses aren't really constrained, right?
Yes, the responses are dependent on the application that you look at.
Can one proof be like, even assuming Enk is secure, one of your responses is the secret key? KOKR secret?
Yes. Yeah, that would be a counterexample of a scheme. Yes, this would be a valid proof. Yeah.
Is the intuition for why, I mean, Chris gave an elegant counterexample, but like, is the intuition in general for the reason why CPA security is not sufficient is basically like, I think you were hinting at this, that the fact that you choose the in ciphertext, but then the challenger goes and deciphers it and does something with the deciphered text, and in that process, the process of them deciphering it, you may learn something about the secret key that you wouldn't in the converse, where you can send them the plain text and they encipher it.
Yes. Yeah.
Okay.
That is a good intuition. Yeah. All right. Other questions? Then let's go into concrete examples, and I think this will also make the general setting or type of these attacks more manageable. So the first type of attacks, or the first set of attacks, is on OpenPGP, which PGP stands for Pretty Good Privacy, and it's a standard to secure electronic communication and data. It's mostly used for encrypting emails, but there are also some use cases for secure storage and data authentication. So I have another question for you. You can discuss with your neighbor, if you ever used PGP before, how you liked using it, and what's the problem with this XKCD. So I give you 2 minutes to discuss quickly, and then we're returning in Plenum.
It's like 20 different.
No, actually, I don't know.
I use it in my password manager. But I don't interact with it. Like I just enter my password and it encrypts my password. So like I think, I mean, it's like I have like a friend who tries to like sign his like doing installs, and like I mean the joke here is just like no one bothers to see this.
Like PGP. Yeah, I mean, I guess mostly in like package managers.
Oh, I can't remember.
That's not something they will ask. Like they will ask you to like query their servers for like to check that the
I mean, there's
keys
also
are valid. Like, yeah, the signatures are valid. Yeah.
authentication, not just like encryption.
Like if you just see that somebody is using PGP, then like you're fine.
So I mean,
I think something like that. There's some authorities, like I guess, right? Like
to automatically
Miro?
verify.
like there like
Exchanging
there's
keys
like
sounds like a pain.
what we were discussing is that
Do you ever use PGP?
PGP is kind of like based on
Like I've read 20 papers.
it's based on like what is it like? Just some guy has like the real truth, or like we are gonna crack or
I mean, there are
Whether
attempts to crowdsource, so that you don't have trust. Like I meet you, I verify your key, and I sign your key, and someone trusts me that I'm sufficiently verified multiple people.
Interesting.
They then transitively trust the keys that I signed.
Yeah.
But in practice, it's mostly a server that provides the public.
It used to be like parties where like
Yeah.
I just want to exchange their public.
Right, I think we can resume. So any opinions on the usability or security of OpenPGP or PGP? Or what's the problem with this XKCD? All right.
One quick thing is that you can just steal and reuse this whole message.
Yes. So they're checking the text. What they should really be checking is the signature, which is a cryptographic operation. That's just terribly hard to do in PGP. All right. Maybe the security, I guess most of you know this. PGP has been heavily criticized for the security because they use outdated cryptographic primitives. They have very complicated data structures, and they're using things that are not provably secure. So they have their own construction of authenticated encryption. That is not actually the one everyone else is using, so that it doesn't have a proof. And it's also really hard to use. So there's a ton of papers on the usability problems. However, it is still very much used and actively developed. And one of the reasons for this is that people build front ends on top of PGP that hide away the complexity and ugliness. For example, ProtonMail, an encrypted email provider, they are a front end basically for PGP that uses this in the backend. And there's also a standardization effort of IETF to update the primitives of PGP to use more secure primitives. So there's still a lot of active work going on, and so that's why it still makes sense to break PGP in 2022. Yes.
Good question. Are PGP and GPG similar as the acronyms that?
If I recall correctly, but someone can correct me if I'm wrong, is GPG is a tool, like a specific application that implements PGP.
Oh, okay, I see.
Yeah. And OpenPGP is such an open source specification. All right, so we're going to break OpenPGP, but we're going to break the DSA digital signature algorithm in OpenPGP. So let's quickly do a reminder of lecture 12, where you looked at the DSA algorithm. So we have a secret key X, and we pick we pick a big prime P, and we have an order Q that divides P minus 1. So you have group or Q. Q is also pretty big. And then we have a hash function that maps arbitrary messages into this group. And basically, we're performing the signature by mapping a message into the group and then building something on top of the discrete logarithm problem to build a signature for this message. So in particular, the operations are recalled here. I will repeat them later on where we need details of them. But this is the same thing in lecture 12 already. So maybe one thing to note here is in the sign operation, we have those. There is a uniformly random value, K, that is sampled and that is used to hide, or that is used to change signatures, basically. But if you know this value K, then you could also compute the secret that is used to sign things. So it's very important that this K is thrown away and not recoverable. So let's see how this is used in OpenPGP. So we see here the data structure that they're using for DSA. And the white boxes here have no cryptographic protection at all. And the gray boxes have cryptographic protection. That's a little bit broken, but not what we're going to break in this attack. So one problem if you don't protect the integrity of the white fields is that we have things like the modulo P, Q, and the generator G in this unprotected stuff. So the adversary can overwrite these things, and there is no check, no integrity check that will fail, because those are just not protected. And since we are doing key overwriting attacks, we're definitely going to overwrite stuff there. So let's look at an attack that's pretty old. It's from 2022. Well, it's sort of the baseline for this line of research that we recently rebooted and revived. So We again have a client server setting. The client at some point generated a secret key pair and uploaded this to the server. And the server now can override the public key. It can't override the secret key because the secret key was part of the part of the data structure that's somewhat protected, syntaxically protected. So we're not going to try to break this. So yeah, the server can override the public key, and the server can observe signatures. Because recall, we're using this for PGP, and mostly it's used for signing emails. So as a mail provider, you see the email, and you see the signature that's attached below the email. So you see both the message that's sent and the signature. So what could possibly go wrong? Does anyone have an idea? What could go wrong if you have DSA and the adversary can pick which primes which subgroup is used to perform operations before the client completes the signature? Doesn't need to be a full attack, can just be a vague idea.
Could you pick a prime that has really small queues for which you can then basically do CRT to reconstitute some kind of thing like that, where you can figure out they raise something to the secret key in that small subgroup queue or a order queue, and then you just do CRT on it eventually.
Very good approach. Very good approach. I guess we don't need the hints. Very nice. So yeah, let's look at how this works a bit more concretely. It's a variant of this, but it definitely goes in exactly that direction. So what the server can do is it can pick a prime where p-1 is smooth. So it has small queues. In fact, it has only small queues. It has only small orders. And the reason we're doing this is because discrete logarithm is easy in this group, because you can do the Pollard row, the Poly-Kalman attack, where you just solve discrete logarithm in all the small subgroups, and then you combine them with CRT, as Cole said. So the other thing we're doing is we're picking Q larger than P, which is completely bogus. There is no valid use case or valid set of parameters that would ever do this, because Q needs to be smaller than P for every normal setting. But since OpenPGP clients don't check for this, we can set it to be larger, and this turns out to be useful. And then we set the generator to be the generator of this group that we picked with a smooth order. And so given a signature, we can now recall this equation here that comes straight out of the DSA signature algorithm. It's computed mod Q below here, but since we picked Q to be larger than P, this value g to the k mod P is already smaller than Q. So this mod Q never does anything, so we can just throw it away. And that means the value R that we get in the signature, so the signature here includes R, is just g to the k mod P. And since P is smooth, we can now compute discrete logarithms in that group, so we can recover K. And once we have K, we can just compute the secret key, which is a problem for this team. All right, so in summary, we have an attack that works with a single signature. You don't need more than one signature. You have one R value. You just you override the public key so that you're in an easy group. You get one R value, you recover the random K value that you're never supposed to see, and you recover the secret key. It doesn't matter that the original key material of the client was generated for a group where discrete logarithm will be secure, because the client actually uses their secret key in your bogus group. So you can just pretend that it was picked for that one. Mitigations are pretty simple in this case, because, for example, our Q value is huge. Normally, it is a factor of p-1, and normally it's around 160 to 256 bits. And in our case, it's more like 2000 bits, which is easy. And also, if you would validate the secret key and public key that you get, you would also avoid this kind of attack. But since it's so easy to cheaply detect this attack, that's exactly what the clients do. They just sort of check for this queue size, and if queue is not clearly way too big, then they're continuing to do their operations. So most libraries right now are not vulnerable, but only because they restrict the sizes of parameters. In fact, so one thing they don't do is they don't integrally protect all the fields in the data type that they're using, which would be the proper mitigation. But it would also mean you need to change the standard, and everyone that implements this needs to change their implementations, which is a very slow process. So instead, they're opting for just checking the parameter sizes. Which brings us to 2022, when some people actually from Proton Mail in Switzerland and the cryptography research group in Switzerland, they were looking into this again. And basically the question they're looking at is, can we do the same type of attack that we just looked at, but without requiring a huge queue, so that we can bypass this easy check that libraries are doing? So let's recall here the verify and unsign operations from DSA. And the way this attack works is basically they pick a prime such that they have an order that's not that's around 16 bits. So you have a subgroup that's not too big but also not too small. And then you basically pick a generator in that subgroup, and you're overwriting this. So now this Q is a factor of p-1, which is correct. It's just way smaller now. Instead of way bigger, it's now way smaller than a normal Q, but the libraries check for it to be too big. And since you're in a smaller subgroup, the discrete logarithm problem also becomes easier. And the way you can do this here is you can check every possible value for the secret key, which is here the secret key in this subgroup. So since the order of the group is QI, you take the actual secret key mod QI. But since QI is small, we can just try every possible value for XI. And for the correct value, the verification for the signature needs to succeed, because it was a correct value, and it doesn't matter that you reduce it to a smaller prime, it still needs to succeed. But for invalid values of the secret key, there's a very high probability that this check will not succeed. So basically what we're doing is we're trying all possible values from 0 to QI. And if the verification succeeds, we know that this is with a high probability the sample or our secret key mod QI. So question to you. If we have a bunch of samples xi are equal to x mod qi, how do we recover the full secret key x mod q, the original q? Anyone have an idea? Very similar to Poly-Kalman. And your homework.
Is it just CRT?
It's just CRT. Yes. So basically you have a bunch of samples mod QI. If you have enough of them, that's the product of all QI is larger than Q. You can recover the original secret key by doing the Chinese remainder theorem.
In practice, how much do you need? Like, what is the sum of all those QI going to be in like in an average case?
So they're picking, that's exactly the trade-off for why they're picking 16 bits here for QI, because that is sort of in the sweet spot where you get big enough samples, but it's not too hard to compute the discrete algorithm. So I think Q was said to be between 160 and 250 bits. So you would need to have 250 divided by 16 QI values. There's not a lot.
But then for each of those, you take QI messages in order to find the value, right? Or
The nice thing is,
it would be like QI over 2, right?
the nice thing is that you can do this verification, you can do offline.
Oh,
Because verify, everyone can execute verify. You
Oh,
only
okay.
need the public key and the signature. So you need to do those 10, 15-ish queries, interactions with the user to get enough QI values that the product of them is bigger than Q. And then you do those computations for 2 to the 16, basically, for every one of those offline.
so if you had more computation power, you could reduce n at the cost of having the offline part increase in complexity.
Yes, I think so. I think there was some other constraints that made them pick this type of value. There's some other, either it's a formatting issue or there was some other constraint in the paper that makes this a bit harder. Because otherwise, I think 2 to the 16 is easily computable.
Yeah.
So otherwise they would probably have pushed it further to get the number down. There was another question.
Just remind me how big is P here?
P is around 2000 bits.
So like, what I'm wondering is, yeah, like kind of the same question for each one of these queries, how many options do we get in the end? Like, yeah, for each one, like how much do we reduce the possible secret keys for each one of these?
So you get a value for the secret key that's mod a 16-bit value. So you're basically reducing the entropy by 16 bits, I think.
Yeah, so it's like 2000 minus 16.
Well, the secret key, so the secret key is taking mod Q,
Yeah,
and Q is only 160 to 250 bits. So you basically have 250 bits, and then you do the first one, and then you have 250 minus 16 bits.
yeah.
And you do the second query and so on. So you're losing quite a lot. Within 10 or 20 queries, you have the secret key.
Okay.
Because what matters for the secret key is Q and not P. Right. There's much more in the paper. There you can do across the algorithm attacks. There it turns out that they're using different algorithms, for example, ECDSA, but you can pretend that they're DSA and then use the same attack to recover the secret also for ECDSA. It's quite neat. They have some more attacks and mitigations discussed in the paper. Have a look. All right. We those are questions if someone else has another question. If not, we're going to attack a different application, which is Mega. So Mega is an end-to-end encrypted cloud storage that has almost 300 million accounts, and they're storing over 140 billion files. So although you might not know them, they're sort of right below the huge players in the market, like Google, OneDrive, iCloud, and so on. They're the 5th biggest cloud storage provider. And unlike the others, with maybe the exception of iCloud, they actually claim to have end-to-end encryption. So they claim they know nothing about your data, and they can't see it, they can't recover it. And basically, in our attack, we show that they could attack the user and recover their files with a key overwriting attack. So let's look a bit into the design of Mega, because this is sort of a bit a more complex example now. So we're looking at the context in which we are executing this attack first. So how their system works is pretty simple. If a user wants to upload a file, they authenticate to the server. They have a file. They pick a file key, a fresh random file key for that file, and encrypt the file with that key. And then they use their password to encrypt the file key itself and upload this encrypted file key to the server together with the encrypted file. Now, this is the point where I was referring to before, why would we ever encrypt the key and then also upload this encrypted key to the server? One of the reasons is if you want to download your file, say from your mobile phone, but you uploaded it on your laptop, you need to somehow get this fresh random key that you generated on the laptop. You need to get that key on your phone. So the way you can do this is by uploading an encrypted key to the server, so that on your phone you can authenticate again to the server. You can fetch the encrypted file and the encrypted key. You can use your password that you just enter when you log into your application on the mobile phone, and then use this to decrypt the key first, and then use this file key to decrypt the file. So that way you can transfer the key from your laptop to your phone. The other thing that turns out to be really useful for the attacks is the authentication procedure. So we're looking at how authenticate works in a bit more detail. And for that, we also first look at how registration works. So to register a user, the user generates an RSA secret key pair. They use their password to encrypt the RSA secret key. Again, for the very same reason as before, if you want to decrypt your files on a different device, you also need to have your RSA secret key again on that device, so you're outsourcing it to the outsourced server. The user during registration uploads the public key and this encrypted secret key to the server. Looks very much like a key overwriting attack, or like the same setting as for a key overwriting attack. For authentication, the user sends an authentication request to the server, and here is sort of where things get weird. Server sends back the encrypted secret key, as we would expect. Also the public key, I didn't write it down here. But the server also encrypts a challenge for the public key. So the server picks some random value, encrypts this for the public key, and sends it to the client. The client then uses their password to decrypt the secret key, and then uses this secret key to decrypt the challenge, and sends this decrypted challenge back to the server. And this is sort of intended. So the authentication succeeds if the decrypted challenge is actually the challenge that the server picked. And this is sort of intended to prove that the client actually recovered the secret key. So that the client was able to decrypt. They know the same password that they knew beforehand, and they're able to decrypt whatever the server sent to them. It's also, interestingly, a decryption oracle, because the server can pick any ciphertext and ask the client to decrypt it, and the client will return something to the server, which is a very weird design and not how you should design your cryptography. But it's a very interesting cryptographic puzzle to make use of this. So we're going to exploit this authentication procedure because it looks the most fishy of those those four protocols. So does anyone have any idea how we are going to exploit this? Given that we are doing key overwriting attacks, what are the points that you would look into further if you were the one that was trying to break Mega? Any suggestions? Which one of those messages would you try to attack, and why?
Also requires one. I mean, logging process. The logging process of this data.
So the answer is no, but this is the entire login request. So the login procedure. So this entire thing is the login procedure. An auth request just means I am user B, I want to log in. And then the things below happen. So there is nothing, or there is a little bit more going on there, that's it. But like the important things of the authentication happen here. Basically, the server considers you authenticated if you are able to decrypt the challenge, because that means you need to know the password of the user. Like in normal authentication, if you know the password of an account, then you are the user, or whatever the server is concerned.
Yeah, the CH Each message maybe.
The CH, do you mean the challenge here or the C sub CH? Challenge.
I think no CH prime. The
CH prime.
yeah.
Because it is the decryption of the ciphertext. That's or why would you target this message?
Because what you said of like the server at some point checks if like the user has already authenticated some or like has already like the key or whatever, and like maybe I think yeah, it's kind of like what I thought could be the point where you could.
Definitely one thing that we're using. I'm going to continue, I guess. So what we're attacking is the encryption of the secret key together with CH prime. Because the secret key is encrypted key material, which is useful for key overwriting attacks. There is another place where there's encrypted key material, which is the encrypted file keys, but they turn out to be very short. So you have just a 128-bit value. You override it; it's a random 128-bit value, and the encryption is some garbage. And it's really hard to learn something useful out of this garbage. So that's why we're not attacking this part. But it turns out that the secret key here has an interesting structure that we use for our key overwriting attacks. And the reason we're attacking this is it doesn't have authentication, so we can't play games with it.
So is the goal here to learn the password that the user is using? From like if you can learn what the secret key is, then you can learn the password, and with the password you can then decrypt any arbitrary file. Is that the goal? Or
the goal here is for the moment just to decrypt the secret key.
Okay.
To get the secret key. You can't get to the password from the secret key. In fact, none of our attacks gets the password. But you can decrypt files.
Wait, how can you decrypt files with the secret?
It's not obvious.
Okay.
Yes. It is a second attack that we unfortunately won't have time to discuss today.
Okay.
But it's building on top of the knowledge of the secret key.
I see. I thought that the secret key was only used for registration. That's why.
Yes. It is used in different places in their system. For example, if you share a file with someone else, you encrypt it to their RSA public key.
I see.
And so those shared files are immediately compromised if you have the secret key.
I see.
But this is sort of like an outdated part of their system that's not really used anymore. But the really impactful attack is the combination of this with another attack where you can decrypt file keys.
I see.
But for that, you need to know the RSA secret key to do the other attack. So this is sort of the first step that you need.
Okay. So TLDR, it's non-intuitive, but learning the secret key is useful to us.
Yes,
Okay.
that is exactly it. All right. So we are going to look at outsourced key ciphertexts, but the file keys are not that useful. So we're going to exploit the encrypted secret key, RSA secret key. So let's keep the authentication protocol in mind. So I'll keep it up there. And to exploit the RSA secret key, we need to know a bit more about the structure of it to know what kind of games we can play. So here is the structure of the RSA secret key in their data format. They store first the prime factors Q and P. Then they store a secret exponent D here, and they store some U value that is useful for decryption. So the way they're doing decryption is RSA CRT, not something we really looked at in this lecture. But on an intuitive level, you can do a faster decryption in practice. If you don't decrypt mod N, but you instead decrypt mod P and mod Q separately, and then combine the solution with the CRT to get a solution mod N. The reason this is faster is because P and Q are smaller integers. They're like we have huge integers here, and they're only 1000 bit if you're using a 2000 bit modulus, and big integer arithmetic is slow. So this turns out to be faster. That's the only reason they're using this in practice. The CRT equations here is what they're using in their clients. It's a bit different than how you learn CRT, but if you compute if you compute the numbers, it turns out to be the same. All right. Yeah. So, does anyone have an idea? What I didn't point out, what I should have pointed out, is they're using AES-ECB to encrypt their secret key, which is very well known to be the best possible encryption for your key. Of course not. So this is AES, where you don't chain your blocks. You just split your message into 16 bytes, and then you encrypt every byte independent of the other, or every block independent of the others. It's no CBC mode, cipher blockchaining, where you actually chain your blocks together. You just encrypt everyone on its own. It has a very famous problem where you encrypt the image of a penguin, and the encryption of the penguin is still the penguin. Because you just map, if it only has like 3-4 different colors, you just map every color to a random block, but of the same color. Every single block of black will become a single block of a yellow pixel. And so you still see exactly the image. But this is not the issue here that we're exploiting. We're exploiting a different issue with using AES-ECB. So does someone have an idea of how we can just in general tamper with this secret key? Because one thing AES-ECB definitely doesn't provide you is integrity. Think about that the signal blocks here are encrypted independent of each other.
I guess you can swap blocks around, but I don't know how that will be helpful.
So if you swap blocks around, you swap the corresponding plaintext bits around between P and Q and D and U, which is a good approach. You can do an even a simpler approach. You can just garble them. You can garble them, and then you will garble the plaintext. You don't know what it is, but also if you swap around blocks, you didn't know the plaintext before, so you don't know it after. It's sort of the same in the end. You just garble a value. Now we're looking at what happens with the decryption if you garble some value. And so notice that one thing is, since those blocks are encrypted independent of each other, just because I garble some blocks in the U value doesn't affect the secret exponent or the primes, which is nice because we want to factor n. Basically, we want to recover the primes. So if everything would be garbled at the same time, then we have a problem because we lose the information that we want to recover. Was there a question somewhere? Okay. So let's see what happens if we garble U. If we garble U, then here in the CRT, we have some random value that's multiplied to our result, which means we get a random result. Doesn't look very useful at first. But it turns out that if you pick a challenge that is smaller than P and Q, the decryption still succeeds. So we're going to look at how. So recall here, we're decrypting mod P and mod Q. But since the decryption is unique, mod P and mod Q, if the value that you encrypt is smaller than P and Q in the first place, then the decryption mod P and Q is the actual decryption of the message already. So both of them are already the challenge that was encrypted. Now, if you place this into T here, you subtract the two values. So T is 0, because both of those values are the challenge that you subtract. Then you multiply your random value by 0, which is very nice because then it falls away. And so the overall decryption also succeeds. And that means you get a correct result. The only caveat is that the way Mega's system works is they have some padding. And in fact, they have the challenge CH prime that they return is somewhere up here, and there's a ton of padding in the end that they just throw away. So your challenge here, if you pick it as such a small value, which the server in normal operation would never pick, it's just thrown away as part of the padding. And the actual message that's sent back is 0. Because if you have like a short integer and you pad it with zeros to get the full size, or like you turn it into a byte string that's the full size, you pad it with zeros. So that's where the zeros come from. All right. So in summary, the server overwrites some of the ciphertext blocks and garbles the U value. And then if it picks a challenge that's bigger than the primes P and Q, the returned challenge value by the client up here in the up there in the authentication protocol, the CH prime returned by the client is a random value. If the server encrypts something that's smaller than both primes, the return value is 0. So now the question for you, if we have sort of this higher level oracle here, now we're abstracting away how decryption works. We're just performing this overwriting, and then we get either a random value back from the client or we get 0 back, depending on whether the value that we encrypted was bigger or smaller than Q. How do we recover the secret key? Or how do we recover the primes PQ?
Search for
binary search. Yes. It does perform a binary search where if you like your entire interval for primes, you start with that, you pick the middle value. If it's bigger than your primes, you go with the lower interval. Otherwise, you go with the bigger interval and you continue. So this requires 512 login attempts, which in this case sadly means the user actually needs to enter their password 512 times, which was definitely something Mega was very quick to point out in their blog post. No one has actually been exploited by this because you would have needed to log in 512 times. Fair enough. We improved the attack rate, or Keegan improved the attack to 6 login attempts afterwards, which is hard to claim that no one logs in more than 6 times unless your service is not used. And then we recovered it to 2 login attempts later. So the attack got better. It also got much more complicated.
Just a question. So you're garbling U in this case, but I was wondering if instead you could exploit AES, the fact that it's not chaining, to zero out one of Q or P, and then somehow recover. Like I don't know, maybe that's not helpful to recover the information, but it feels like if you force the value of CH to be 0 mod Q, then you'd be learning its value mod P, and maybe you could try and reconstruct P from that.
Yes, that is a great intuition. So let me point out the problem with this approach. We can't, to find a block that decrypts to all zeros, we need to know the key. The only thing we're doing here is we're changing it to something random, and then the decryption is something random. And we would need to be really lucky for it to be all zeros. Or we would need to know that one of those blocks in the format is already decrypting to all zeros, but unfortunately there is none of these blocks. However, in our second paper where we broke their patches, we actually found an encryption oracle. So we found a different part of their system where we can give it some plaintext, and it will give us the ciphertext for that. And there we started playing exactly these games. 0 and 1, or like an all 0 block, doesn't turn out to be the most efficient solution. But yes, so if you can override other parts with something you know what it is, this is really powerful, and you can also break the system with that. Which is actually how we got down to 2 queries for 512. So absolutely great intuition. Yeah, there are 4 more attacks in the paper in 4 where we, among other things, also extend this attack to actually decrypt files. Because right now we only have the secret key, but you can build on top of this attack with something that is also partially a key recovery attack, but also some other type of attack to recover files. So yeah, as I already hinted, Mega didn't really mitigate the way we suggested them to mitigate. So here, as an exercise for the class, how would you mitigate this attack? It is not what Mega did, I can promise you that. But how would you try to protect against this type of attack? if you were in the shoes of Mega and you just received the preprint of our paper and the 90-day deadline to fix your system as part of responsible disclosure before we're going to publish our paper, what will you do?
Yeah, how expensive it is to change EBC or like
What would you change it?
I guess to CBC or whatever thing, like change, I don't remember exactly the name, but like whatever don't allows you to do this kind of attack.
Yes, which would be an authenticated encryption mode, for example, AES-GCM. That's a great suggestion. It means every user needs to log in and re-encrypt their key, because Mega can't change the encryption. Definitely something we recommended them doing, and they didn't do it. If you would change the file encryption, we calculated in our paper, and it would take over half a year to do this. So this is really expensive, but changing the key encryption would maybe be feasible. So that's why we suggested it to them. But sort of the problem that everyone would need to be online, and if you're not online until a certain deadline where the code is removed from lines and you stop supporting this type of key, then you're just losing access. This was too much legacy problems that would come for them. They would potentially lose users, and they didn't want to do that. That's why they didn't do it. So instead, what they did is they just added some validation to your secret key. So basically similar to what Alex suggested in the beginning, is that can I just look at my key, and if it looks weird, probably the server is playing some games, so I'm refusing to continue operating. So that's what they do. In particular, they're checking whether U is the inverse of Q mod P, which is because we were changing the U value, and in fact our attacks don't work if you change any of the other values. So they just checked for this value, and it prevents our attack. But we were not really satisfied because it wasn't really what we suggested them to do. And in fact, what they didn't do is protect the integrity of the encrypted secret key, as you suggested, by changing AES-CCP to AES-GCM or some other authenticated encryption. So the problem with this approach here is that if they validate, the client leaks whether a key was valid or invalid. And so it turns out that this gives an error oracle where you can play games with the key, so that it sometimes passes this check and it sometimes doesn't, and depending on secret information about the key itself, it passes or doesn't pass the check by using this encryption oracle that we found, that we already talked about with code before. So we're basically maliciously modifying the key such that it's a really easy special case that sometimes passes this validation check and sometimes doesn't. Some of the errors that we get back are coming out of their big integer library, because they also implemented that one wrong. So that was really useful. Yeah. So let's see my library. All right. So yeah, in summary, what are key overwriting attacks? The threat model for key overwriting attacks is we have a malicious server that stores encrypted key material of the client. In our case, it was always asymmetric key material, but it could also be suspected material. It runs some interactive protocol with the client. It can overwrite those keys and then observe computation or client. And the goal of the server is to recover. So examples of this in the wild of this key overwriting attacks occurring is OpenPGP, where we looked at the Maposa attack from 2022, which is basically the base version of this, where you just change the public key. And then with a very bogus big Q value, and the attacks from 2022 then improved on this by not using such an obviously wrong Q value. And then we looked at the mega attacks where we covered RSA secret key. There's also an error oracle in the second mega paper. So yeah, with that, I am at the end of this lecture.